In this section, we're going to learn about taking the derivative of the logarithmic function. Recall that the definition of the log function is that it's the inverse of the exponential function. So log base b of x equals y if and only if b to the y power is equal to x. So log base b of x tells you the power, the exponent that you have to put on b in order to get x. The derivative of the log base b function, the derivative of log base b of u, is equal to log base b of e divided by u times du dx. So there's the basic form, right? Log base b of e over u, and then of course we always have the chain rule at work. Here e is Euler's constant. That's the base of the natural log. Note that if we're taking the derivative of the log base e of the natural log, it's just 1 over u times du dx, because of course the log base e of e is equal to 1. We're going to find it helpful to review some properties of logs, to use these properties sometimes to rewrite functions. For starters, we'll note that the log base b of a product x times y is log base bx plus log base by. In other words, if we're multiplying inside a log, we can split it up as adding the two logs together. Similarly, in item 2 here, if we're dividing inside a log, we can split that up as subtracting the two logs. And these work in both directions, right? So if I were adding two logs, and I would be able to combine them as long as they're the same base, right? So log base b, we would be able to combine them and write them as a single log. And then the third one's my favorite, log base b of x to the r. If I'm raising something to a power inside a log, I can bring this power down in front as a factor in front of the log. Let's get some practice. We're going to find dy dx where y is equal to log of 4x. Now if there's no base written, it is understood that it's base 10. That's the common log. So using the formula, dy dx is going to be log base 10 of e, or just log e, over 4x. And then the chain rule has me multiply by the derivative of the stuff inside, so I'm going to multiply by 4. Note that the factors of 4 cancel here, and we have log of e over x. It is far more common to encounter natural logs than the log of any other base. Anything that you can model with an exponential function or a log function, you can model with a log base e or an exponential base e. And as you can see in the formula up here, the derivative is just a little bit simpler if we're working with a natural log. So you'll see natural logs more than the logs of other bases. Let's find the derivative for this function. Note that there's not a lot of space given here, so it's not going to take a whole lot of work. In fact, I'm going to show you probably a couple different ways we can do this problem. But the first way is we'll just, our function is y equals ln of 3t to the 4th. So that's my argument inside the log. Now, I can't bring that 4 down in front right now because it's not the entire argument that's being brought to the 4th power. And if I want to just jump in and take the derivative, I can do that, right? The derivative of ln of stuff is 1 over the stuff. So 1 over 3t to the 4th. And then I'll multiply by the derivative of the stuff inside, so that'd be a 12t cubed. And then we'll reduce. So 3 goes into 12 4 times. T cubed cancels. So I just have a t to the 1st in the bottom left over. We get 4 over t. I said I'd show you a couple different ways to do this problem. If you were looking at this and thinking, oh, I could use properties to rewrite that, well, we couldn't bring the 4 down in front initially. We'll just note that we're multiplying inside. That's 3 times t to the 4th. So I could first split it up as ln 3 plus ln of t to the 4th. And then for this, in the second log here, now I can bring that 4 down in front. So we've got ln 3 plus 4 times ln of t. Now I haven't done any calculus yet. This is still just the y function. But now let's find dy dt. Ln of 3 is a constant. It's whatever exponent I have to put on e to get 3. It is a constant. So when you take its derivative, that is 0. And then we have 4 times the derivative of ln t is 1 over t. The chain rule would have us just multiply by 1. And we get 4 over t. Now, using these properties in this instance probably didn't make for less work, right? I mean, it was pretty simple to just start right off taking the derivative and just reduce the fraction. But they are equivalent to each other. Now, in the next example, we're going to see where it really is a lot easier to take advantage of these properties of logs. If we look at example 420, this log, inside the log I have x times the square root of x plus 1. I could jump in and just take the derivative, right? 1 over the stuff and then the chain rule. When we use the chain rule, though, we'd have a product rule, and it'd be a product rule that involves parentheses to a power, and we'd have to do a bit of algebra to simplify, which is nothing that we couldn't handle, but an ounce of algebra is worth a pound of calculus. So I'm going to start by rewriting this function. First of all, this is multiplication inside, so I'm going to split it up by adding the two lns. So ln x plus ln of, and this square root I'm going to write as the 1/2 power. And now I'm going to take this 1/2 power and bring it down as a factor on that ln. We've got ln x plus 1/2 ln x plus 1. Now when we take the derivative, I don't have any product rule to worry about, right? I'm going to take the derivative with respect to x. We get 1 over x plus 1/2 times 1 over x plus 1. The chain rule would just have us multiply by 1 in both cases, so I'm leaving that off. And I'm going to get a common denominator. The first fraction needs a factor of x plus 1. The second needs a factor of x. Oh, you know what? The first one also needs a factor of 2, right? Because of this 2 right there. So now my denominator is 2x times x plus 1. Up top, I've got 2 times x plus 1 plus x, which is 2x plus 2 plus x. And this is 3x plus 2 over 2x times x plus 1. There's our derivative. So we still had some algebra to do to simplify. However, it's a lot easier, I think, at least, simpler algebra to do than what's involved when we have to execute the product rule that we would find ourselves doing if we just jumped in to take the derivative and needing to apply the chain rule there. Okay, let's do another. We're going to find dy dt for the function y equals ln of sine squared. So this is sine squared of t, means sine of t all squared as a function. That means that we can take this power, right? It's the whole argument that's being squared inside. So I can bring that power down in front. So we have 2 ln of sine of t. Now if I take the derivative, I bring down the factor of 2. Ln of sine of t. So the derivative of ln of stuff is 1 over the stuff. So there's 1 over sine of t. And now we're going to multiply by the derivative of sine t, which is cosine t. So we have 2 times cosine t over sine t. But cosine t over sine t, that's equal to cotan of t. So we have 2 cotan of t is equal to dy dt. Now, one cool thing that we get when once we learn about derivative of the log function is, so we know how to find the derivative. when we're just given a logarithmic function. However, sometimes some functions might be easier, or we might find it helpful to impose a log function when there was none before. And we call this process logarithmic differentiation. We're going to do a couple of examples, so I'll kind of show you the process that's sort of laid out here in this procedure that's listed. I'm going to show you the process in these two examples. This first example, we already have another way to do it, and you might think that way is easier anyway, and that's fine. The second example will be one where we have no other way to find the derivative other than to impose a log on both sides. So let's get started. The first step says you take the natural log of both sides. So here's my function, y, and I'm going to just rewrite it, x times x squared plus 1 to the 1/2 power. So I'm going to start by taking ln of both sides. So ln y is ln of x times x plus 1 to the 1/2. I can split this up over the multiplication. Oh, and that was x squared plus 1 in there. X squared plus 1 to the 1/2. And then bring this exponent down as a factor in front of the log. So, the first step in logarithmic differentiation is take the ln of both sides. So, we start with an equation, a function that has no log involved in it, and then we impose the log. We say, you know what, I want this to involve logs. And the only reason that we would do that is because we will find it useful to use those properties. So that's the second step, which we just did, which is use those properties to kind of split up this log. Here we split it up over the product, and we brought that power down in front. And then once we've used those properties to rewrite the ln, then we'll differentiate. We're differentiating with respect to x, and on the right side, that it's like a regular function with logs. So there's not much special going on there. On the left side, though, this is ln of y. So we have to think of it as an implicit differentiation problem. The derivative of ln y will be 1 over y times dy dx. On the other side, I got 1 over x. Plus, I've got that factor of 1/2 and then 1 over x squared plus 1, and then the chain rule here would say multiply by the derivative of x squared plus 1, so I'm going to multiply by 2x, cancel those 2's. So 1 over x plus x over x squared plus 1. And this is all 1 over y times dy dx. We're going to simplify the right side, so I'm going to just add these fractions, get a common denominator. The first one needs an x squared plus 1. The second one needs a factor of x. So we have x squared plus, so on the denominator, I've got x times x squared plus 1. There's our common denominator. Up top, we have x squared plus 1 plus x squared. So that is 2x squared plus 1 on top over x times x squared plus 1. So we've simplified the expression for 1 over y dy dx. We want to solve for dy dx, so I'm going to multiply both sides by y. Now here's the thing. When we do that, I'm going to come up here to finish this out. When we do that, on the right side, let's just look at what we have here on the right side. I have this expression that has both x's and y's, right, and this factor of y. But the original function was given y as a function of x only. So when we find dy dx, we ought to be able to write it only as a function of x. And so what we're going to do in our next line here, right, on the left side, definitely, the y's cancel, so I just have dy dx. On the right side, I've got 2x squared plus 1 over x times x squared plus 1. And then instead of saying times y, I'm going to replace y with the function that I know it's equal to up here. And then do some simplifying here. I can cancel this factor of x. Also on the bottom, I have this x squared plus 1 to the first. Up here, I have an x squared plus 1 to the 1/2. So when they cancel, I'll be left with a 1/2 power in the bottom, or in other words, a square root in the bottom. Now this is the same simplified result that you would get if you had just started and instead of taking ln on both sides, just jumped right in and did the product rule, and then did the simplifying, the chain rule and simplifying that goes along with that. So we already had another way to do this example, but this sort of shows you how logarithmic differentiation works. Taking the ln on both sides, I think, made this step of just taking the derivative easier because there was less chain rule to worry about. We just had more algebra to do later on to simplify the final result. Without taking the ln on both sides, that just sort of puts a lot of the algebra right in this process of differentiating, and we had to do more calculus, more like chain rule, more product rule to worry about. This next example, though, says find the derivative of the function y equals x minus 1 raised to the sine x power. We have no rules that help us find this derivative because we'll just note that the power rule does not apply. Okay, so the power rule does not apply because the power rule, which says the derivative with respect to x of u to the n equals n times u to the n minus 1 times du dx, in the power rule, n has to be a constant. And here, it's not a constant, it's a function. So we don't have a rule yet that tells us what to do when we have a variable in the exponent. In the next section, we'll look at exponential functions, but even then, that rule won't help us with this function because with an exponential function, your base has to be a constant. So here we have a variable in both the base and the exponent. And in situations like that, this is where logs really shine. This is the moment logs were like designed for, to kind of help us rewrite this function in a way that is more manageable. So I'm going to start. Here's our function, y equals x minus 1 to the sine x power. I'm going to take the ln of both sides. The whole reason I'm taking ln of both sides is because I'm going to take this power, sine x, and bring it down as a factor in front. Now, on the right side, we can take the derivative here. We're just going to use the product rule. So our f function is sine x. That means that f prime is equal to cosine x. Our g function is ln of x minus 1. And so g prime is 1 over x minus 1. So putting together the derivative, let's see, on the left side, we have ln y. So on the left side, when I take the derivative, I'm going to get 1 over y dy dx. On the right side, the product rule, g times f prime, that is cosine x times ln of x minus 1. plus fg prime, that is sine x over, or sine x times 1 over x minus 1. Now we want to solve for dy dx. So I'm going to multiply both sides by y. Oops. It's plus. Here I'll just combine that as a single fraction, sine x over x minus 1. And then instead of times y, I'm going to replace it with the function of x that y is equal to, x minus 1 to the sine x power. And you know, there's not a lot you could do to simplify this. If you wanted, you could distribute that, but I don't think it really makes it much simpler. So I'm going to leave the result in this form. So here's a function that without logarithmic differentiation we would have no way to find the derivative, but now if we impose logs on it, all of a sudden we have, our techniques will work and we can find dy dx.